Thank you very much. So today I'm going to say a little bit about various joint works on this project that's been going on for about 10 years, which is almost finished. I'll try to say that later. Classification of these things in algebraic geometry, but it's using techniques from algebra. And so it's not actually going to be an algebraic geometry talk. It's going to be focusing more on the algebraic aspects. But I want to begin just by saying a little bit about the motivation, because the motivation is important for a few different things that I want to say. So what are we trying to do? Yeah, so I need to set up some language. So we're trying to classify a particular surgery in algebraic or birational geometry called the threefold flop. So we want to classify surgeries. So what does that mean, and what do these surgeries look like? And so the easiest example of what's called a flop is the Atiyah flop. And so how do you build this as an object? So you start with a commutative ring at the bottom, the C, U, V, X, and Y, and you have a single equation that UV is equal to XY. Yeah. Single equation. So you're inside a polynomial in 4 variables. You have a single relation, so you're down to a 3-dimensional ring, threefold. Yeah. And so given this ring, there's an isolated singularity at the origin. That's a calculation that can be done. Yeah. Now, typically, if you go from surfaces, you could blow up that origin. You could do that in birational geometry, but we're not doing that. Instead, we make a choice. And so we blow up this ideal u comma x. That's something you can do. That's allowed. And if you do that, and it's a calculation, it's not something that should be obvious. But if you do that, you end up with a space that's smooth. It's quite remarkable. And it's got a single curve, P1, above that point that you started with. And everywhere else, it's an isomorphism. So that's a calculation. Yeah. So then you stare at the equations and you realize, well, u comma x is a complete symmetry here. I could have blown up u comma y, and it shouldn't be surprising given the symmetry that you're going to get the same answer. And so you get this scheme here, which again is smooth, which again has a P1 over the origin. So you don't have to repeat that calculation because symmetry tells you it has to be true. Yep. And so here's the point that these two schemes, x and x plus, they are the same, right? Just by symmetry, you haven't done anything. But there is no isomorphism which is compatible with these two blowdown maps. Yep. So they're isomorphic as abstract varieties, but not as varieties over the base. So there's no connecting isomorphism. And so this is the first example of what's called a flop. Yeah. So what's the distinguishing features of a flop? And so you have a curve in some sort of variety, and you squish it down to a point so you can blow it down somehow. And then you blow it up, and you extract a curve in its place. It's like a surgery. So you replace this curve by a different one, and it's not the identity operation because they're not compatibly isomorphic over the base. There's technical things, but that's the basic upshot. And just as a part of language, this morphism here and this morphism on the right, they're both called flopping contractions. And the birational map between them, x and x plus, is called the flop of the red curve. Okay, so that's what we're interested in threefold flops. And so here's some questions that you might ask about them. So why is this hard, right? So I want to do that by analogy because analogy comes back later. So when you start doing finite dimensional algebras, you begin by a class of objects that somehow are representative of the general difficulty. Yep. And so if you started by looking at finite dimensional algebras by only studying the complex numbers, you might have an unreasonable viewpoint of how easy its representation theory is, right? The representation theory of the complex numbers is, it turns out, significantly easier than the representation of an arbitrary finite dimensional algebra. And just as that's true in finite dimensional algebras, I'm going to try to make this analogy precise later. The Atiyah flop is an unreasonably easy flop. It is by far the easiest one. Yep. And so why is it hard to build these objects? So to build it, you need to, so in the way I described there, you need to construct something, so some ring, and the sort of, it can't be a unique factorization domain. So you have to be able to pull things out. And so how you measure something's not a unique factorization domain is using something called the class group. And to pull out exactly one curve, you absolutely need to make sure that the class group is Z. And there's a small issue there that there is no known algorithm to actually compute you the class group. Nonetheless, you need to ensure that it's exactly Z. And as soon as it's Z, you have two distinguished objects, +1 and -1, inside those objects. And so you blow them up. So that's not so bad. You can calculate that usually. But typically that doesn't give you a smooth variety. And so you need to be able to blow it up and ensure you're smooth. So condition 1 is really, really restrictive. And condition 2 is really, really, really constrictive. And condition 3 is the crazy one too, that usually you don't get a single curve above the origin. You get some sort of higher dimensional object. And most of these are that you aren't even graded. So the difficulty is in constructing them. Somehow it's a sequence of things, each one harder than the other. And so when I started this project, it's remarkable how few flops were in the literature. So how many flops are there? Yeah, so we're now in the stage where we can classify them. But the question really, before you think, can you classify them, is how do you discover, construct them? How would you go about constructing such a thing? Yeah. And the whole point of the talk really is that the technology you need to discover and construct flops is the same as the technology that you need to classify them. So actually we're jumping from basically very little is known to full classification, which might seem like quite a big jump, but it's not really. It's just because the way you should construct them somehow needs the technology of the classification in some sense. So I'll try to explain that to you later. Good. Okay, so there is a plan in this talk, you'll be pleased to know. And so the plan is that the first part, I'm going to talk about the abstract part of the classification. So you have these objects that you want to understand, and you reduce the problem to a problem in finite dimensional algebras. That's good. It's very abstract. But it's a key reduction step. Part 2 of the talk is talking a little bit about this actual classification. So you actually do classify those finite dimensional algebras, and you build the geometry, and you say lots about that. And then part 3 is bonus corollaries that come out sort of all towards the geometry. So it's not just the fact that we're classifying for its own sake. Of course, we're really classifying because we want to know those consequences that come from it. Okay, so good. I'm 8 minutes in. Perfect. Yeah. I should say I've given this talk in person before. I've not done it online, so this could go. Yeah. If you've been to my talks before, it's going to go similar. Good. So here is, I need to describe to you the contraction algebra. So that's the kind of key bit of information that's going to take us from algebraic geometry into the world of finite dimensional algebras. And when I'm giving a talk on this, there's a problem in that there's many different ways to construct this object. The easiest, fastest way is the one that's on this slide, but it won't be clear to you that's intrinsic. The other method, which is on the next slide, is intrinsic, but is much, much, much more technical. And so bear with me, I've got 2 slides to take you through some things about this. So this one here should be conceptual and nice and simple, and the other ones should be a lot more technical. So we're going to study threefold flops today, and just to classify them. So smoothness is going to be important because smooth points are somewhat classifiable. And there's only going to be one curve above the origin. That's not going to be mission critical for most things, but it just simplifies my life in giving a talk. So here's the cartoon picture. It's the same cartoon picture as before. You have some base ring, you have an isolated singularity. Out of that isolated singularity, Gorenstein, there's assumptions, this curve comes out. And because the fiber is one-dimensional, Michel van den Berg, back in 2004, showed that the derived category of X is actually the same as the derived category of some algebra. Yeah, so there's a tilting bundle on this algebra. So the derived category of X is the same as dB of this this algebra, and that algebra is infinite dimensional. It's a 3 Calabi-Yau algebra, coming from the fact that the geometry is Calabi-Yau. Yep. And so what we do is we say, well, that's a very large object, so we just slice it. So we take a quotient of that large object, and by all those morphisms that factor through the ring. And so in representation theory, that's known as the stable endomorphism ring. So ACON, instead of looking at this large object, you basically lose all information essentially. You factor out this, and you factor out by R, so you've the stable endomorphism ring, and that's finite dimensional algebra. So that's good, but for 2 reasons. The first reason is you've got a mechanism of taking in a flop and outputting a finite dimensional algebra. That's good. The second reason it's good is that these sort of objects behave well with homological algebra. They interface well with homological algebra. Endomorphism rings are things that functors go to naturally. But the sort of downside of this slide is it involves massive number of choices, right? There's loads and loads of choices of derived equivalences to lots and lots of different rings, right? And I've just chosen one and unilaterally declared that I have a contraction algebra. Yeah. And so this is good from many perspectives, but it's not intrinsic. And so I want to try to convince you that actually it is intrinsic. Okay, and so I have taken all the technical details out here to save people. So the contraction algebra can be defined using deformation theory. And so deformation theory is a sort of wonderful thing in that it tells you that you're doing something intrinsic to the geometry that you're in. So there's choices involved in deformation theory, but it is intrinsic. And so there's a second way I'm not going to explain today that you can define this contraction algebra using deformation theory. And the absolutely wonderful thing about this is it's clearly an intrinsic invariant of the curve. We haven't chosen tilting bundles, we haven't done stuff. Actually, it's just completely intrinsic, and therefore you should expect it to be controlling other numerical invariants of curves. But the downside of this viewpoint is it's very hard to control deformation theory from the viewpoint of homological algebra. Yeah. So this is why in the rest of the talk you will not see deformation theory appearing until the end, is that typically the homological algebra is controlled by tilting and things like this. So it takes the first definition, but all the consequences, like the numerical invariants, come through the deformation theory. So it comes in right at the end. And there's only two facts you need to know today. That since there's only one curve, the contraction algebra is a factor of the power series, non-commutative power series ring in two variables, x and y. So you should think of that as the free algebra in x and y, but you're allowed infinite sums. That's all. Yeah. And actually, even more can be said that since it's smooth, this is the title. The Jacobi algebra, the contraction algebra is a Jacobi algebra. So it exists some f, somewhat difficult to say what it is, but there is an f. The contraction algebra is the Jacobi algebra. So just to clarify what that means, there's some f that if I differentiate it with respect to f, differentiate it with respect to y, and I take the two-sided ideal generated by those, I have to close it. There's a technical closure issue to deal with the fact these are not Noetherian, etc. You take the closed ideal, which you can ignore, and that's what's called the Jacobi algebra. So this is coming in from things that look like they come from cluster theory. Okay. So this was the conjecture with Will back in 2012 really. So if the conjecture was saying that these finite dimensional algebras classify, they're the classifying object. Yeah. And so if you have two smooth threefold flops, they're all smooth, I'm suitably local, so I can possibly classify complete local. And if you have two contraction algebras, then of course you can't tell which side of a flop you're on. So the way you think about quality is if the bases are isomorphic. So this is on the left-hand side is three-dimensional geometry is completely controlled by the isomorphism classes of finite dimensional algebras. Yeah. And this is the hope at the time was there's a huge reduction in complexity, that this is three-dimensional, this is somehow zero-dimensional. And so really, if this was true, you'd have a hope of understanding what general flops look like. And indeed, it is true. And so it is now a theorem due to many people. And so we'll talk to it a little bit. So the fact that this implies this is just the fact that deformation theory is functorial. So that's back in the original stuff with Will. And then the converse went through a sequence of reduction steps, first through Jenny August's thesis, then through some observations of Carl Yang, then Hua Keller. And then finally, the very last step was produced by Yasso and Muro. And there's a turn to this last step, which I'm going to talk about in the next few slides, due to myself, Joe Karmazyn, and Emma Lepri. So it's a theorem, but I want to try to explain to you why it's a little bit surprising, the theorem. Yeah. And I want to do this by an outrageous analogy. So I want to take you back and pretend that we're in the 1890s. The 1890s was a remarkable time. one thing that was remarkable in the 1890s, among other historical facts, is what the isomorphism theorem for rings was not yet known. Yeah. And so my understanding is that the first time it appeared in print was Emmy Noether's theory of ideal domains. Was the first time the isomorphism theorems for rings were in literature. And so imagine we're back in the 1890s and we have an injective ring homomorphism from A to B. Yeah. And seems like an outrageous analogy, but just do bear with me. I'm not patronizing you. It becomes important in the next slide. And so if you have an injective ring homomorphism, what were you to do? Yeah. Because they're not the same, right? A and B are not the same ring. Yeah. And so there's a shiny new technology of the time, coming from linear algebra, called the image. And so what is the image? The image is the solution to the problem, what you have to do to make it an isomorphism. Yeah. So there's something inside B called the image, which A is then isomorphic to the image. Yeah. Now, this is a disaster if you're emotionally attached to B. Yeah. So our first isomorphism theorem has got nothing to do with B, right? A is isomorphic. What is the image? Well, the image is the stuff that comes from A, right? I mean, it's all about A. The image is A, and all you're saying is that the things that come from A are A, right? And so if you like B, this is a problem, and that's going to be a problem in the next slide. And all we're doing is asking a very modern take on that question. Yeah. So let's just say we've got a slightly more complicated situation, like a morphism of unital DG algebras. Yeah. So unit. So I want there to be a unit. Yeah. Yeah. And so I have a morphism of DG algebras, and instead of saying it's injective, which of course is a little bit it's not maybe the right thing to do, you instead say, okay, I'm going to assume it's injective on cohomology. Yeah. And so how would you make that the same, or a quasi-isomorphism? How would you do that? Can you do that somehow? And so that's the question. And we don't actually answer this question, but we answer a similar version to this question in the situation. Yeah. I should say that the picture comes from, I Googled subsistence farming Europe, 1890s. And I was expecting a French picture to be the first one, but this is Sweden. This is Swedish farming in the 1890s. So they're also dealing with primitive technology here, and that's that's supposed to. Good. So why is this relevant? Why am I telling you about the 1890s? Yeah, here we are. So it's all about B. Don't be too emotionally attached to B. So in this setting, if you believe the conjecture is true, which I've given you absolutely no evidence that you should do that, but if you believed it was true, what you have to do is be able to build this 3 Calabi-Yau object just using the isomorphism class of acon. So you have to have some construction. It takes you acon, which is not Calabi-Yau, it's finite dimensional self-injective algebra, and somehow it constructs for you some 3 Calabi-Yau objects. And would you believe that's reasonable or not? And so let me just explain why you might not believe that's reasonable. So here's the 3 Calabi-Yau object you have, or you want to build. This is A. This is A. Yeah. And by the derived equivalence, this object that you want to build is really the endomorphism ring of some really nice projective resolution. So this is a lovely, lovely projective resolution. And since acon is a factor of the NCCRA, there's a very natural functor. You just tensor the projective resolution term by term over A with acon, ring homomorphism, restriction, extension of scalars, and you get to this B, the R end of acon, and that's just saying you take this and you tensor it term by term, this. And you have A going to B, which it turns out is injective on cohomology. Yeah. And so here's the point. The contraction algebra clearly builds this object, but the first isomorphism theorem is not about that object. It's about the image. Yeah. And so if you're emotionally attached to acon, which I am, throw it out there, and in particular you can build that object, you've got a problem because you think it's going to be quite difficult to prove this conjecture, Because if you believe it, there better well be an intrinsic characterization of the image, whatever that means. Yeah. And now homological algebra and images aren't the best of mates, right? They don't really sort of go well together. And so, there's cones and things, but images are not somehow that. And so if you look at this slide, you'd probably be tempted to think the conjecture is false, because you're trying to construct something as a sub-object of something you understand. And the first isomorphism theorem for rings tells you that's unusual. Okay, that's the end of my outrageous analogy. Go back to do some maths. Yeah. So here's the solution to the problem, or a solution to the problem. In this situation, you can pass to the strictly unital minimal model. So this is A infinity algebra stuff, right? So here is the B that I'm very emotionally attached to. And this is the thing that's built from Acon. Yep. And so that's a DG algebra. And so somehow I view going to the minimal model as like presenting it. Yeah? So you present it by generators and relations. So here's your vector space. And of course, you present it at the cost of having lots and lots of higher multiplications. So this is the infinity formulation. So that's something you can do, yeah, or can be done. Yeah. And inside this space, because it's strictly unital, I have a unit. There we are. There's my unit. And I just look at the vector subspace that's spanned by the unit and all the positive cohomology. Yeah. So in some sense, it's a very naive thing to do. You somehow, in some sense, you're truncating. You're not quite truncating. You're certainly throwing away the negative stuff. You're making the degree 0 thing precisely the unit, and you're taking the positive part of it too. And this is a remarkably easy lemma that for absolutely any, by any I mean that I'm only studying those DG algebras that have got cohomology, right? So every DG algebra that ever appears in nature has that property. But you've got to be careful because some DG algebras have got no cohomology. But basically every DG algebra, this A infinity structure restricts to this object. That's just a very, very easy check you can do it just comes down to the definition of the infinity structure, essentially. And so in particular, you have a canonically defined subalgebra. Yeah, canonically defined subalgebra, which has an infinity structure on it. Yeah. And the second very easy lemma, which is very believable, is that if you have a morphism of unital DG algebras, that gives you a morphism between its minimal models. And actually, because it's taken the unit to the unit, it's not entirely surprising, that restricts to give you an A infinity isomorphism between these two subalgebras. And I want to just sort of pause and say this is a very easy lemma. As in, if you're into symplectic geometry, a lot of people can do this in their head. I find this amazing, or alarming, depending on your viewpoint. But this here is called we call this the unitally positive thing. And we'll just explain the name. So we can't call it the non-negative because the 0th part isn't exactly what you think. So it's got the positive part and the unit. So it's the unitally positive. That explains the name of the algebra. Okay, and so given that extremely easy lemma, let me just explain to you why the conjecture is true, right? And so you've got two flops and you've got an isomorphism of contraction algebras. And then you pass to the B's that I'm very emotionally attached to. And so you have these two DG algebras, and they're not even quasi-isomorphic, they're actually isomorphic as DG algebras. It's an incredibly strong property, but we don't need that, but they are isomorphic. So here's your B1 and here's your B2. And it's a morphism of DG algebra. So you apply the extremely easy lemma and you get a quasi-isomorphism between these unitally positive things, right? That's just a very easy lemma. Yeah. And because essentially these are the images of the morphisms from before, you take these objects that you have and it turns out that they are quasi-isomorphic to those. But that's really just a statement of the fact that the thing you had before lands in this subalgebra. And it comes down to the fact that your two vector spaces of an injective map of the same dimension have to be isomorphic. And it's simple as. So this 3 Calabi object here is the same as the 3 Calabi object here. So it turns out to be exceptionally simple in the end. And so I'm just really here to advertise this object, this subalgebra. It does appear, so Julian Kohlschammer emailed us after we posted to the archive. It does appear in some highest weight stuff too, there in slightly different context. But this is tells us the key object. Okay, good. So that's the abstract classification and the sort of technology that we need to go into that. Yeah. So I should pause because I realize I'm probably going far too fast here. Yeah. Any questions so far? No. Good.
Hey, I have a question.
Yeah.
Hi. Sorry. I'm a bit confused about the degrees. So you said that any quasi-isomorphism between A and B B and B1 and B2 restricts to an infinity in this n B1 and B2, but it seems like counting the degrees, one of these A infinity maps could land in the negative degree part of B. So
Yeah,
do
it's
you
a
just
it's a degree calculation. So we make, and maybe I'll answer it like this. We make no claims that if you take an arbitrary A infinity morphism, then it restricts. We make no claims of that. We only make the
all
claims that
right.
the DG ones come down, and that's the key. Yeah.
I see.
And it
Okay,
could,
okay.
there's mixing issues in general, yeah. But the fact that it's the DG, that's the claim.
All
There is
right.
probably a more general version of it, but we only need the DG. So that's it. Yeah. Yeah.
Okay, thanks.
Oops. Okay, and so let me pass to the actual classification then. So then we're down to the question, we're interested in classifying flops. We're only thing we have to do now is understand what these contraction algebras are. That's it. And if you understand what they are, then you win and you've classified 3-4 flops. Okay, so first of all, the first thing to say is that these algebras are local. Yep. If there's a single curve, it's a local algebra. And in representation theory, local algebras aren't famous for somehow being accessible by representation theory means. Let's put it that way. And so there's benefits of being local, but there's downsides too. And I'll try to explain some of them as we go along. So first of all, before you think how we're going to do it, you ask yourself the more general question: why do you believe it should be possible? Right? So here's the sort of the key challenge, right? In some sense, the contraction algebras are algebras that come from geometry. That's where they come from. That's their definition. They're defined to be all objects that come from geometry. That's the definition. And how are you supposed to classify such things before you know what the geometry is? Yeah. Yeah. So of course, you solve this problem by classifying something else, and at the end, it turns out that you've classified the thing that you thought of. Yeah. And so how we do this, we've got a shiny bit of technology called the algebraic length. And so I just want to talk you through that technology and what it does for you. It's a little bit surprising to me still. Yeah. So just to set this up, so we're going to try to take an abstract Jacobi algebra and give ourselves a number. So this is going to be a little bit tricky. So to do that, I just need to remind you of a bit of notation. So we consider the following ADE Dinkin diagrams. So they're all of them there, all ADE Dinkin diagrams. And what I've done is, on top of the ADE Dinkin diagram, I've dumped on the data of the highest root. Yeah. So if you see what highest roots are, that's great. If not, just think of this as completely random numbers that I'm giving you associated to the things. So, but it's key, it's important that every vertex has a number associated to it. Right? So this vertex here's got a number 2, this vertex here's got a number 3, etc. Yeah. Now, to every ADE Dinkin diagram, there is a pre-projective algebra associated to it. Again, it's just a canonically associated algebra. It's got some relations, but that's not important for now. But it's some canonically defined algebra, which happens to be finite dimensional. And just how quivers work, the vertices of the graph are corresponding to what's called primitive idempotents in the pre-projective algebra. That's just quivers. Yeah. And so in particular, each of these idempotents, these primitive idempotents, comes equipped with a number. Yeah. So if you're in the pre-projective algebra of type D, and I choose this idempotent, it's coming with the number 2. That's all I'm saying. If I'm in this pre-projective algebra, I'm doing this idempotent, it comes with the number 3. I'm just associating a number to idempotents in the pre-projective algebra. And so here's the absolutely key algebraic definition. So I'm going to say an element in the power series ring in two variables. So there's lots of elements in the power series ring in two variables. I'm going to say it's got algebraic length L for some number between 1 and 6. If I can find a single central element, so Z is in the center of the Jacobi algebra, such that the quotient of my Jacobi algebra by that central element is E pi E. Yeah. For some ADE pre-projective algebra and some primitive idempotent, which has got this associated number L. Yeah. So I just try to unpack that for you. Of course, it's certainly not clear that such a central element exists. Right? So if it doesn't exist, we say it's purely algebraic. So somehow it doesn't come from geometry. Now, again, this will talk you through. So if there exists something in the center, it's not clear the center is non-trivial, incidentally. But if there is something in the center, and it's E pi E for some ADE and some idempotent with some number L. Yeah. And the key point of this definition is that it's really not clear that it's well defined, right? Because it's all about a single central element, Z. Right? And it's perfectly plausible that you have two different central elements that are different slices to different E pi E's. That actually happens. Yeah. And the claim is that it might well happen, but the numbers are always the same. Yeah. And so that actually is probably our main theorem, is that this algebraic length is well defined. Yeah. So again, I'll just spell it out. So if you have any two central elements where the first slices you to one E pi E and the second slices you to a different E pi E, that's fine. That is allowed. Yeah. It doesn't matter. The numbers associated to the E1 and E2 have to be the same. Yeah. And I'm not going to lie, I've dumped a lot on the math community over my life. The proof of this theorem is where all the pain lies. This is a purely algebraic statement. Yeah. And I'll show you we prove this by partly using the classification of flops of length 1 and 2. We use a lot of analytic changes of coordinates, and we use a lot of numerics of knitting calculations for ADE Dinkin diagrams. And somehow, I'm just sort of appealing to the community here. If there is a lovely algebra-only proof of why this is true, this would vastly simplify what we're doing. I'm not convinced it is possible to find such a proof, though. In some sense, my view is that this is somehow the manifestation of Miles's general elephant conjecture, which is a theorem, in the algebraic setting. And that takes a lot of doing somehow. But the proof of this is brutal somehow. It's, you have to analytically change coordinates a lot to be able to sort of rule things out. And that's not fun. But once you've got it, once you've got the theorem, you're on a winner, because now you have an intrinsically defined invariant associated to a Jacobi algebra. And in particular, it solves many isomorphism problems. So if you've got two Jacobi algebras and you want to know, are they isomorphic or not? If one of them's got algebraic length 1 and the other's got algebraic length 3, then because algebraic length is well defined, they cannot be isomorphic. And that's the kind of one of the key things that the technology does. Anyway, we get a number out of it. Yeah.
Can I ask a question?
Yeah, sure. Yeah.
So in your definition, it's not clear what is the role of this number L. So can you say a little bit more?
The number L is just it's coming to the fact that imagine if you slice to E pi E on this vertex of 7, and it is possible to slice to E pi E on a vertex of E8, for example. That can happen. But it just says you must slice to this one or this one. That's all. The number 3 is that if you slice an E pi E, the only other E pi E's you can slice to are the ones labeled by, say, 3. That's all. So the number itself isn't so important. It's just the fact that it's a way of saying that, of ruling out other slices happening, I think.
So simply these numbers, in order to avoid kind of obvious isomorphisms, right?
Yeah, so this is part of the
problem. So simply these numbers are not important. Simply says kind of number encodes when you've got obvious isomorphisms. Sort of.
Yeah.
like that. Yeah, okay, thank you.
It also solves a little bit of a subtle point that the e pi e here for this 3 and the e pi e for this 3 aren't isomorphic. They're not. But that's okay. It's still number 3, and that's all we're doing. Yeah. Yeah.
And why it is called algebraic length? Because it's really confusing.
Yeah, so I'm going to try to explain that later because it turns out to recover a different invariant from the flop side later called corollaries length.
Okay, sorry.
The algebraic version of length. Yep. 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 Okay, and so the strategy then is you got some canonically defined thing, and so you just classify those, right? Classify all the f that have got a particular algebraic length. That's a purely algebraic thing. So there's no geometry on the slide that I'm showing you. This is a pure, fiercely algebraic thing. Yeah. So what's the theorem? Is that if you have something of algebraic length L, yep, and the Jacobi algebra is finite dimensional, then actually very few things can happen. Yep. So up to analytic change of coordinates and other pretty grim isomorphisms, only the following things can happen. And this should feel very similar to sort of simple singularities, ADE sort of singularity theory. That's the sort of feel it should do. So if you've got length 1, you have a particular form x squared plus y to the n. If you've got length 2, something that's d4 in some sense, and you've got this thing that looks very much like d4, there's some conditions, it's not so important. If you have length 3, you have a particular form where this is a polynomial of order bigger than or equal to 4. If you've got length 4, you have this form, where this means you can have absolutely anything you want in degree 6 or higher. We can actually improve that, but I just don't want to make the slide that technical. It's not that important. 5, you have this form. Again, you have you can choose whatever you want there, but you can actually make it nicer. And 6, you have this form. Good. There's some conditions. But the point is, it's a little bit surprising that it is actually possible to classify these algebras. That's what they are. Yeah. So a few remarks that I need to make, partly because I'm going very fast, so I want to slow myself down a bit. So the first thing is that it's that implicitly in here is a few facts. So here's a polynomial, and one of the things that polynomials have are coefficients. Yeah. So you have continuous parameters, right? So in length 1 and 2, there are no continuous parameters. There's no coefficients, right? It's just 1, right? The coefficient is always 1. Whereas here in length 3, you can choose coefficients on this polynomial, and that gives you non-isomorphic Jacobi algebras. So what's happening here really is that there are continuous parameters, or moduli in the more technical term, in length 3 and higher. So there's uncountably many things here, and only countably many things at the top. Yeah. But that's somehow, there's a tension there, so you think there's too many of them somehow. But the miracle is that numerics comes to save you. So the Jacobi algebras in 1 and 2, the dimension varies quite a lot. I mean, we know what it is, but there's a formula somehow. In dimension 3, there's not much can happen. The dimension just depends on this number n. The Jacobi algebra, the dimension just depends on that number n. Yeah, it's something like 4n plus 10 or something. I don't know. There's a formula. But the kind of miracle, and this is where you need standard bases, is that absolutely every Jacobi algebra of algebraic length 4 has got dimension 60, independent of what you choose here. Absolutely every Jacobi algebra of length 5 has got a dimension 125, independent of what you choose here. And absolutely every Jacobi algebra of length 6 has got dimension 200, independent of what you pick here. And so although there's uncountably many of them, numerically there's very, very few. And that's in some sense what saves you in this whole game. That having uncountably many is great somehow, but your numerics are very constrained. And this is exactly the opposite of what happens in surfaces. So in ADE, the A and D are your big families, and there's only 3 examples of type E. Here it's the opposite. A and D are somehow your small families, and your E is some uncountable zoo. but it's not really a zoo. It's quite tame. And so the second result is a triumph of typesetting over mathematics. So all I'm going to do next is I'm going to ask, okay, what about those that have algebraic length that are infinite dimensional? Yep. So all that's going to happen in the next slide is this symbol is going to change to an equals, and things are going to move slightly. So let me do this. I'm very proud of myself here. Give me this moment. Give me this moment. So here we go. Yeah, there we go. So I'll go back just to check that we haven't tricked you. So go back to that's what it was before. Yep. And all I'm doing is I'm moving to the next theorem. And so the Jacobi algebras of algebraic length L that are infinite dimensional, there are basically none of them. Yep. There's a single example of length 1. There's a single countable example of length 2, and then a sort of another single example length 2, and precisely one example length 3. And that is it. Yep. And just one thing that we have no explanation for whatsoever is if I do go back to the slide, whenever I see an n on this slide, I'm going to push it to infinity. Yep. If I push this n to infinity, this goes away and I get x squared. Yep. Similarly, I see here and I push n to infinity, this goes away and I'm left with this. Here I push n to infinity, I'm left with this. Here if I push n to infinity, this goes away, I'm left here. And here against numerically, there is no n, and so they all just go away somehow. And so that's somehow, the classification of infinite things are all limits in some way we cannot make precise. That we don't use that in the proof. This is somehow comes out at the end. There are limits of them, but they're basically none. And so this is the algebraic thing. This is all written down. We're all very happy with this. It's all very lovely. And it turns out there's just many fewer than you sort of might naively expect. Okay. So I want to just now talk to you the geometry version of this. So since this is the motivation, that's an algebraic result, but it has geometric consequences. Yeah. So this is ongoing, and I want to explain why it's ongoing, because the last bit I just talked about is written. So here we have an object of algebraic length, and the Jacobi algebra is finite dimensional. And our claim is that actually that is a contraction algebra of some smooth threefold flop. So this is afterwards you've classified something algebraic, and we have to convince ourselves that everything in that classification is a contraction algebra. And we have to give you a construction of a flop given anything on the previous two slides or previous slide. And we do that, but we're struggling to make that human readable at the moment. That's quite a complicated calculation. It's true, but being able to write that down in a sort of finite number of pages seems complicated. We're getting there, but that's why it's ongoing. And then this is coming back to Vlad's question earlier. Once you have part one, once you do know that this classification is the classification of flops, it turns out this algebraic length invariant, this number, we have to call it algebraic length because actually it equals something from the geometry called Collar's geometric length. And so this is just saying your numerical invariants are matching, which has to be somehow. And the classification of threefold flops follows. And in particular, all the numerics that I tried to explain 2 slides ago, all that constraints come immediately across the curve counting, and you get a huge number of corollaries just from the constraints that come from the contraction algebra, so numerical constraints that come from them. Okay, so yeah, very good. And here's the type E flops admit moduli continuous parameters, and here's my precise statement. So you have 2 Jacobi algebras here and here, and you just added on a thing alpha. And so these Jacobi algebras are isomorphic if and only if alpha is 0. So you do get these continuous parameters. They happen in all the other cases too, it just becomes more technical. But yeah, continuous parameters exist. But that's okay, because numerically they're constrained. Okay, and so the next slide is just to be careful what you wish for. If you go back to my original, slide. So how we build the geometry is we do not write down the commutative ring R. That's not something that we do. And this is trying to explain to you why we don't do that. So for the Atiyah flop, It was UV is equal to XY. The birds were singing. It was all lovely, and we constructed the Atiyah flop. Yeah. So this is an example of, I think it's a length 5, maybe length 6 flop. And this is one of the few ones we do know. And as you can see, the equation of the base is somewhat more complicated than UV is equal to XY. And the thing that you blow up in the class group, I think, has got 7 generators. It's a really, really complicated, explicit thing. Yeah. But nonetheless, I mean, so this is why we don't construct them in this way, because it's just not human readable to see something that looks like this and convince yourself, oh, yes, that's definitely the base of a threefold flop. So we give data in different data. We give you how to glue the top space as opposed to the bottom space. But just let me show you why you should believe this is related to flops. If I circle where X is in these diagrams, so these are all the terms that involve X. Yep. And if I quotient by X, which should feel very similar to quotienting by your central element, lo and behold, you get Y5, Z3, and T squared, which is an ADE singularity. Yep. And so this is, again, this is the geometry version of the algebraic length earlier, that really these quotients by central elements are some ADE sort of type behavior, and they're really explaining what's going on. Yeah. But yeah, so basically, I know this is not an algebraic geometry seminar, but normally when I give these talks, I get moaned at that I'm not telling people the equations of R. And this is just to defend on the fact that you don't want to know the equations of R. That's somehow the point. Yep. Yep. Okay, and there's a couple of bonus corollaries. There's not many slides. There are 2 slides left, I think. And so so instead of flops, you can also study crepant divisorial to curves, so divisor to curves. So let me explain to you what those are. Here's a cartoon picture. And so instead of this single curve going to a point, the single curve might sort of move in a family. And so you think of this as a sheet of paper. I just squish the sheet of paper down to a line. Yeah, so just this curve gets contracted to a point, that curve gets contracted to a point, etc. So it's a cartoon picture. But because it's a sheet of paper which is 2-dimensional inside something which is 3-dimensional, it's a divisor. Yeah, so this is where the divisor word comes from. And because you're squishing it and it's going down to a curve, the fibers are all 1-dimensional. This is why you're taking a divisor, you're squishing it to a curve, and that's this divisor to curve contraction. Yeah. And so, of course, we could try to classify or understand those as well. Yeah. And I said about 3 slides before that there are basically no Jacobi algebras that are infinite dimensional and have got algebraic length. And so as an immediate consequence, basically crepant divisor to curves don't exist, essentially. And so, yeah, so the theorem is no crepant divisor to curve contraction of length bigger than or equal to 4. And the obstruction to that is non-commutative. Yeah. And so I was a little bit annoyed by this. So I didn't know if this was surprising or not. I was a bit surprised, I suppose. But I don't like it when you prove things, or I prove things that I've got no philosophical reason to expect why that should be true, right? It is a fact now, but I had no reason why it should be true or any sort of rough idea. And it's interesting because Mori in his 1988-1992 papers, he showed that for flips, they also stop at E6. And so I was actually in Kyoto a couple of weeks ago, and I asked him, do you have a philosophical reason? Why should that happen for flips as well? And I'm delighted to report he also doesn't know why flips stop at E6. They just do. And so somehow, obstructions happen. We still don't really know why. But basically, these other crepant divisor to curve basically don't exist. We haven't classified them because we don't have the background theory. But basically, we're expecting very, very few of them. Okay. And then the last consequence in the last couple of minutes is that basically, as a consequence of the full classification and numerics of understanding of standard basis, we're able to tell you absolutely every curve counting invariant, be that whatever you want, numerical curve counting invariant for absolutely any threefold flop. So that could be Gopa-Kumavafa, Gormall-Witten, Donaldson-Thomas. We can tell you every single curve counting invariant for flop. So just talk you through very briefly what that looks like. And so you have, again, your flop and contraction. Here's your cartoon. And I like this from an algebraic point of view, actually. If you have a finite dimensional algebra and you want to somehow understand its dimension, one of the things you can do is you can try to flatly deform it, because that doesn't change the dimension. So you flatly deform your finite dimensional algebra. So you're deforming it. Now, most finite dimensional algebras are semi-simple because semi-simple is somehow an open condition. So you can imagine taking your finite dimensional algebra and deforming it and then breaking into matrix rings. Now, I'm not very good at counting dimensions, but I can count dimensions of matrix rings. And so, you break up your algebra and you break it into simpler pieces. Yeah. And that's exactly the same idea here of what's called Gopa-Kumawafa numbers. So you have some complicated threefold flop with a complicated contraction algebra. And so what you try to do is you try to split it into the simplest possible things. Yeah. Now in algebras, the complex numbers are matrices over the complex numbers. They're the most simple algebras. And they are the contraction algebra of the Atiyah flop. The Atiyah flop is the simplest possible flop. And so what you do is you flatly deform this thing. This is way back to cats and various people. You flatly deform your singularity into the simplest possible things, and they're Atiyah flops. And so your curve splits into pieces, and you actually do count curves on the neighboring fiber. So it is a curve counting invariant in the strictest sense. You actually are counting curves. And so there's this curve invariance. So you count the number of curves in this here that's got a particular numerical property. The numerical property isn't terribly important. But it's the same idea as in algebras. You take your complicated algebra, you flatly deform it, and you split it into the simplest possible pieces, and then do some count there. And so you get some numbers. These are called the Gopa-Kumawafa numbers. And they determine every single other numerical invariant, Gomo-Witten, whatever. That's somehow well known. Yeah. And so what we do, the theorem, is that all these numbers are known in absolutely all cases for all possible flops. You can do as you want. But this is the kind of really remarkable part, is that actually very few things happen. Yep. Very few things happen. So if you've got length 4, for example, absolutely every flop of length L has the same curve counting invariance. Every single curve counting invariant has to be the same. And that's just a sort of manifestation that for length 4, all these Jacobi algebras had dimension 60, all of them, every single one. And so in particular, numerically, you can't distinguish them. And so similarly here, all the flops of length 4 can't be distinguished numerically. And so they have exactly the same Gromov-Witten theory. So curve counting is almost optimally rubbish at sort of determining differences between flops. But it means, in some ways, it means it's a good invariant, right? Invariants shouldn't see moduli in algebraic geometry. And so it's a good invariant. It's just that it's not very good for classification purposes. And so the end is the kind of the hero of the story coming in on a horse in the end. The hero of the story is called as the algebraic length invariant. And so this single number, L, if L is 4, 5, or 6, that number determines absolutely every other numerical invariant. Right? Just a number 4. So I give you a number 4, all other numerical invariants are completely determined by it. And as much disparaged it is. If the length invariance needs to hug somehow, if it's been for like 30 years disparaged, but actually in the end turns out to be the hero of the story, and certainly for higher length determines everything else. Okay, I'll stop there. Thank you very much. Thank you.
Thank you very much, Michael, for that very beautiful talk. Are there any questions? Then please just unmute yourself and ask.
Yes, question about kind of this definition algebraic numbers. So basically, you have your non-commutative algebra in X and Y. You consider arbitrary polynomial, consider Jacobian algebra, right?
Yep.
Which is rather complicated object, I suspect. Right, because you have, Then you're interested in particular factor algebras, so that come from the central elements such that it will be, so on one hand, you have a complicated object, non-commutative algebra in 2 variables. On the other hand, you have Denkin diagrams, and for them, you have nice algebras, so-called pre-projective. And you're interested in the factor algebras, which are kind of Conas algebras for these pre-projective algebras, which come from their idempotence, right?
Yeah.
So my question is, why you choose kind of this definition? So question number 2 in your, just let me finish, because I presume these questions are connected, could be. So why you choose this rather very restrictive situation? which is very nice because the situation is related to the AD classification and all this business. Question number 2. What presumably the role of pre-projective algebras in your proofs plays a role, because you see from that moment you can forget about this factor algebra, simply looking at this Conas algebra. Presumably you work from this moment using kind of these Conas algebras, right?
Yeah.
Okay.
So the first question is we studied this because we knew that contraction algebras had this property. Yeah.
I see.
Certainly contraction algebras were inside there, and so we knew that somehow before we began. But the sort of mystery to me actually was that it's really, as you say, it's a very non-commutative thing. The algebra is non-commutative. And so it wasn't clear to me that you should expect any central elements. To me, it's a miracle.
True. Yeah.
The center is non-trivial, and actually, the center is not even trivial. We know the dimension, and it's kind of it's big.
No, it's just you see, it's a kind of to find a needle in a haystack. You see the central element.
Yep. And I think that's actually how Gavin, my collaborator in the geometry, views it too. Actually, that this number is the thing that, especially from the geometry side, just finds that needle. And you're right, the pre-projective thing, the E pi E, that algebra is the key thing, as opposed to the pre-projective algebra it lives in isn't so.
I see.
But we do think this is more general. This is related to your second question. So if you're doing two curve flops, you should expect the slice to come down to two vertices in a Dinkin diagram. And so we expect some sort of statement to have some sort of we expect some statement that allows us to say the slice is well-defined and you have a well-defined invariant. But you know, that's just a single number is an easy thing to deal with, but multiple vertices becomes more complicated.
But another question, sorry to ask, what is the idea of using this theorem when you have six series of polynomials? So just very briefly, intuitively, how you cut out kind of to this polynomial?
You take there's the philosophical point here for the finite dimensional algebraist. So you take formal schemes seriously. So if you do a finite dimensional algebra, which is admissible relations, we view it not as a finite dimensional algebra, but as a complete local algebra. It's complete.
I see.
So it's canonically filtered by its Jacobson radicals, and we just filter it, and we say, okay, we slice off the fourth part of the Jacobson radical, and we rule out lots of things.
I see.
The fifth thing, and of course, each time you go up the layers, you have to analytically change coordinates to move things. But you just come up the layers, and by the time you get to layer 6, you've managed to rule everything out, and so you win.
I see.
Yeah, but it's only when you do the calculation that it stops, right?
Yes. So after this factorization, after this factorization by the radical 4 powers, every argument are very nice, because you can do this holomorphic, very easy and controllable way.
Yes.
Thank you very much for your question. Thank you.
Okay, are there any other questions?
I had a maybe silly question when you mentioned the moduli, this alpha.
Yeah.
So for different values of alpha, they're also non-isomorphic.
Yeah.
You only mentioned.
Yeah. So there's actually a two-dimensional moduli as opposed to one-dimensional in that example. Two-dimensional. Where is it? Here. So you can add in beta as well, and that's affine line. That's A2's worth of moduli. So you can put beta plus y6, and that's also isomorphic too.
Okay.
So, we're trying to go through working out the dimension of the continuous parameters in each case, but we can't make that human readable at the moment. It's the problem, because you have to be able to write isomorphisms between your 200-dimensional algebras, and we can write them down, but we're not convinced a human can check them somehow.
So these algebraic lengths is more general than Collat's lengths, actually, right? In some sense.
In some sense, yes. It should be, especially when you go to multi-curve stuff, there should be an algebraic way of doing it. I mean, to be honest, I couldn't believe it when we proved that it was well defined, right? So I'm still at that shocked stage that I haven't really internalized what's really making it work.
Right.
I think it's it's somehow, yeah, the fact that a single number starts distinguishing stuff in isomorphism classes is somehow amazing. But equally, it comes back to the all our ability to do this comes that we've encoded standard bases into magma and things that if you view it as a complete thing, you slice and slice and slice. Actually, it's not a bad thing. It's a really reasonable calculation. But only because it stops, I think that's the point. Yeah.
Right. Okay, great.
So the natural question, what is next? Simply,
So we've got well, we need to write a human readable proof of this fact that the flops are buildable. That's we've got it, but yeah, that's the problem at the moment. But that's a minor thing on the grand scheme of things. We think that to me the big problem that's coming is that I think the contractibility of curves is completely determined by the finite dimensionality of the contraction algebra. So what we'd like to be able to say is that instead of having all this algebraic length business, you take an arbitrary Jacobi algebra. If it's finite dimensional, then it's a contraction algebra of a thing, because that's not structural. That's nothing to do with algebraic length. That's just a finite dimensional thing, and that's the big question. And we're getting closer to answering that actually, but it's related to all the fact that Artin's work on surfaces and contraction, that was 1962, and there's basically been no progress. And so, but I think it is the technology that allows us to think about these questions. So that's the big thing that's next, yeah.